everyone, welcome to the second set of PowerPoints and slides for Chapter 8. So we'll be continuing on with talking about electron configurations, and now we're going to use that arrangement of electrons in the atom to talk about periodic trends. And specifically today we're going to talk about two trends. We're going to talk about the radius, and we are going to talk about ionization energy. So that's kind of where we're going today. If you're following along in the regular slides, this is slides 27 to 48, and it will correspond to the Chapter 8 lecture worksheets, pages 3 through 5. Something that I will be using a lot during this set of slides and the next is Coulomb's law. Coulomb's law, and we'll use it, later in the course, but Coulomb's law is the energy of attraction, or it can be repulsion, between two particles, and it's directly proportional to the product of the charges and inversely proportional to the distance between them. And so what this means is this energy of attraction over here. As the charges get bigger, the energy of attraction goes up. You can kind of think of it like magnets. If you have, bigger magnets, then the force of attraction between them is larger. If you have smaller magnets, then the force of attraction between them is smaller. And then the distance here is in the denominator. And the distance, a lot of times we're going to talk about like the radius of the atoms. But the distance between these two different charges, the larger the distance is, the smaller the energy of attraction or the force of attraction, which would make sense again if we're thinking about magnets, right? The closer you put the magnets together, the larger that attraction is, till where you get, if you put the magnets really, really close together, they're going to kind of clink together really quickly, and it's hard to keep them apart. So we want, like I said, I would just think about magnets when you think about this. It's electrical charges, but magnets help us understand it. So like if you had really big magnets, that would be a large force of attraction. And if you put the magnets really close together, right, which would make a very, very small distance, again, that would be a very large force of attraction. So this Coulomb's law, we're going to use this to talk about a lot of different topics in the course. But essentially, as the charges get bigger, the energy of attraction gets bigger. As the distance gets smaller, the energy of attraction gets larger. And then the opposite would also be true. So another topic that we're going to talk about today is penetration and shielding. Okay, so what we talked about last time, right? We talked about the different shapes of orbitals, like 1s, 2s, 2p, and so on and so forth. We talked about, like if the nucleus is in the middle, then the 1s is kind of here, right? It's spherical. And the 2s goes around it. It's also spherical, and it's bigger, right? It's farther from the nucleus, those outer electrons, and it's bigger. We have what's called penetration of the 2s orbital into the 1s orbital. You can think of these almost as like an overlap, right? Where some of these electrons in the 2s can be present in the same space as this 1s, right? And this goes way up there. So this is here, this is called the radial distribution function, and it's essentially just showing the probability of where you're most likely to find the electrons. So if you look, like this is the line for the 2s. So it's most likely that we would find those 2s electrons out here somewhere. But right, we have some probability, right, that we will find them also here, right? There's another probability. And so there's a node here, right? So we could find them here, kind of. We're more likely to find them here. But the fact that we can find them down here in this 1s area is called penetration. And so this radial distribution function shows us that the 2s orbital penetrates into the 1s orbital. And if we compare that to the 2p, right? I know I've got a lot of lines going on here, but this is the 2p, right? There's almost no penetration down here, right? Or very little of the 2p. So it's showing that the 2s orbital penetrates more deeply into the 1s orbital than does the 2p. And so what it's saying is that the weaker the penetration of the 2p sublevel means that the electrons in the 2p sublevel experience more repulsive force. And this is the key, okay? They are more shielded from the attractive force of the nucleus, right? We're talking about electrons here. And electrons are attracted to protons, right? Positives and negatives attract. And so the electrons in these orbitals, these 1s, 2s, 2p orbitals, are attracted to the nucleus. But if you can think about it, the electrons, let's just say like the electrons in the 1s versus the 2s. So the electrons in the 1s, there are 2 electrons that can hang out in there, and they are very close to the nucleus. They are experiencing a large attraction to the nucleus. Again, thinking about Coulomb's law, right? They are very, very close to the nucleus, right? A very small radius, a very small distance. So they will have a large force of attraction. The 2s, even just by being farther out, have a slightly lower attraction to the nucleus because they are farther away. In addition, though, let's think about these 2s electrons. These 2s electrons that are hanging out here are attracted to the nucleus, right? They're attracted to the nucleus, but in the way are these 1s electrons, and these 1s electrons are repelling the 2s electrons. That's when we talk about shielding. That's what's happening. These 1s electrons are kind of blocking the 2s electrons from experiencing the full attraction to the nucleus. Like, you know, if these 1s electrons weren't there, the 2s electrons would be better able to be attracted to the nucleus. But since we have those 1s electrons in the way, they are slightly repelling these 2s electrons and therefore shielding the 2s electrons from the protons in the middle. So if we're thinking then about, and I'm just going to put them kind of out here, if we have our 2p electrons, right, there are 6 of them, 1, 2, 3, 4, 5, 6. So if we think about our 2p electrons are even more shielded from the nucleus because now they have 1s electrons in the way and 2s electrons in the way. So they're experiencing an even more reduced attraction to the nucleus because they're now being shielded by 4 electrons, 2 in the 1s and 2 in the 2s. So here, this last bullet point says, the deeper penetration of the 2s electrons means that the electrons in the 2s sublevel experience a greater attractive force to the nucleus and are not shielded as effectively. So the fact that these 2s electrons, looking at this graph, right, the 2s electrons have this hump here. Some of the 2s electrons, there is at least some probability that the 2s electrons can hang out even closer to the nucleus than the 2p, right? And so that's what we're talking about when we talk about penetration. So that fact that they can penetrate means that they have even less shielding effect from those 1s electrons because they can hang out kind of in the same area. But when we're talking about penetration and shielding, this is what we are talking about. Okay, so here's our order of the orbitals that we were talking about last time. 1s, 2s, 2p, 3s, 3p, and then we start getting into this mess. And if you'll recall, last time I was telling you the d orbitals are numbered differently, right? So even though they're in the, 3rd energy level, they have the principal quantum number 3, the 4s electrons are actually lower in energy than the 3d electrons, which is odd, right? And here's, it continues this, the 5s electrons are lower in energy than the 4d, the 6s electrons are lower in energy than the 5d and the 4f actually. So a couple of reasons why this happens, right? Because of penetration, sublevels within an energy level are not degenerate. So what this means, this not degenerate, that means that the 2s and the 2p are not equal in energy, right? The 2s is lower in energy than the 2p because it is experiencing less shielding. It has higher penetration to the nucleus. This energy level will get filled before this one, okay? The sublevels within an energy level, are not degenerate because of this penetration. The fact that these s orbitals can penetrate farther into the nucleus actually causes them to be lower in energy than the d sublevel from the previous energy level. Okay, and this is because of that penetration, because they have some overlap there. And then as you get, this last one's just saying that as you go from like 4s to 5s to 6s, right, the energy difference between the levels becomes smaller for the higher energy levels. So like the difference between the 4s and the 3d is going to be a bigger energy difference than the 5s and the 4d, and which is bigger than the 6s and the 5d. This is why last time when we were talking about irregular electron configurations, and I was telling you that essentially one of those electrons from like the 4s, so if we had something like this, where it should have been like this, and then 3d, oh, sorry there. So if it was going to be this, right, where the 4s would have 2 electrons and then the 3d would have 4, this electron actually gets excited and instead hops over, so it makes this, right? So we have 4s, 1, 3d, 5. And the reason that it can do that is because these energy levels are similar in energy. The 4s and the 3d are similar enough in energy that an electron can kind of slide over and do this alternate configuration. So this is why we're getting this, because the 4s has a very strong penetration to the nucleus, right, which makes its energy level, or its energy, different. One of the trends we're going to talk about is the radius, and the radius is just like you would describe it in math, right? It's half the distance across the atom, essentially. Here, like the technical definition is half the distance between nuclei and a covalently bonded diatomic molecule. But it plays out the exact same way as thinking about it as just, halfway across the atom. So the atomic radius increases as you go down a group. So if we are thinking about the periodic table, this is going to be my really rough sketch of a periodic table. Sorry, everyone. But if we're thinking about a periodic table, as you go down a group, the atomic radius gets bigger. And this should make sense, right? We're adding on protons, neutrons, electrons, we're adding on energy levels. It makes sense that the atom would get larger as you go down a group. The reason that we get larger is that the valence shell, right, the outer shell of electrons, is farther from the nucleus. Every time we're, going down a group, like going from the 1s to the 2s to the, 3s to 4s and going down the group, that's adding on a larger and larger and larger, s orbital or p orbital, right? And so those outer electrons are farther from the nucleus, which makes the radius of the atom larger. We're going to talk about what effective nuclear charge is really, really soon. But the effective nuclear charge of the atom is fairly similar. The bigger thing that's happening here is that the valence shell is farther and farther and farther from the nucleus. The atomic radius decreases, and I really want to emphasize this. The atomic radius decreases as you go across a period from left to right. And the reason I want to emphasize this is that people get this wrong. So as we are going across the periodic table, the atom is getting smaller. The atoms get smaller going left to right, which should strike you as weird because as you go from left to right, you're having more protons, more neutrons, more electrons. And so you would naturally think, right, and the mass gets bigger, you would naturally think that the atom is getting larger, but it doesn't. The atom is getting smaller. And what's happening is that we are adding electrons to the same valence shell. Okay, so if we're thinking about the atom, this is going to be my nucleus, and let's say here's some, electrons out here. As we, just going to kind of put some electrons, 4, 5, 6, 7, 8. Let's say we're in the third energy level somewhere. As we start adding electrons to this energy level, as we're going across the third period, right, we're adding more and more electrons to this same energy level. And while we're doing that, we are adding more and more and more protons to the nucleus. That's why, so this effective nuclear charge, essentially, the effective nuclear charge, you can kind of think about as being number of protons. We'll get into a better definition of it in a little bit on the next slide, but for now, just think of it as kind of like number of protons. So we're getting more and more protons in the middle, more and more positive charge in the middle, and we are adding more and more electrons to the same energy level. And as we're adding more and more electrons to the same energy level, you're getting essentially more negative charge here, more positive charge in the middle, which draws this energy level, right, and all of these energy levels in closer. So as we're adding more protons to the middle, more electrons to the same energy level, we get a stronger force of attraction. And that stronger force of attraction brings that valence shell closer. So instead of being really, really far out, as we add more and more and more electrons, it actually draws it farther and farther and farther in. So the atomic radius decreases. So you can think about this in terms of Coulomb's law, right? We have a larger charge in the middle, a larger charge on this valence shell, and as we do that, the force of attraction is larger, which draws that valence shell in closer, which makes the atom smaller. Okay, this is probably the hardest trend for people to really talk about and really get their minds around. So that's why I really want to emphasize that one. So effective nuclear charge, like I said, it's kind of related to the number of protons. It's not quite that, but effective nuclear charge is the net positive charge that is attracting a particular electron. And so the way we calculate it, so effective nuclear charge is abbreviated ZEF. I know it's strange. And so the way that we will do this is you'll take the number of protons, right, the total number of protons, and you will subtract out the number of core electrons, the number of electrons that are not valence electrons, okay? And then that will get you the effective nuclear charge. So when you're asked to calculate effective nuclear charge, that would be how you would go about doing it. So if we're looking at atomic radius, like the trends, so atomic number 3, right? And as we are going across from 3 to 10, so this is going across the second period, you'll notice that the atom is getting smaller and smaller and smaller and smaller and smaller, right? Until we get to atomic number 11, this is sodium, right? Which is our 3s now. We've added on another valence shell. We've moved into the third energy level. And so that makes the atom bigger again. We've added on a giant energy level. Then as we add electrons, we get smaller and smaller and smaller and smaller and smaller, smaller and smaller, until we get to the next one. And I believe this is potassium. So then we're adding on another energy level. That would be the 4s, right? The fourth energy level. And as we add electrons, we get smaller and smaller and smaller again as we go across the periodic table. So the largest elements in a given period will always be these alkali metals. They're very large. And then the smallest atoms in the period will always be the noble gases. They're very, very small. So again, this is different from what people might think. So just keep that in mind. I'm going to go back and do one example of effective nuclear charge, just so you can see kind of how it's calculated. Let's say we were going to calculate the effective nuclear charge of magnesium. Magnesium has 12 protons, right? It's atomic number 12, so it has 12 protons. To figure out the number of core electrons, right, magnesium's electron configuration will be 1s2, 2s2, 2p6, 3s2. Okay, that's magnesium. These guys, right, this is the largest principal quantum number. Those are our valence electrons. Okay, so these are not what we are going to subtract out. We want to subtract out the core electrons. So that would be everything else. So 2, right, the 2 plus 2 plus 6. So we add these together, we get 10 core electrons. So we'll subtract out our 10 core electrons, and that would give us a 2 plus as our effective nuclear charge. So here, if you don't like this graph, this is another way of looking at it. This shows you pictures, circles, right? Atoms obviously aren't perfect circles, but this is a good way of showing them. But again, as we go from left to right, as we go this way on the periodic table, our atoms are getting smaller and smaller and smaller, right? The alkali metals over here in this 1A group will always be the largest in the period, and the noble gases will always be the smallest in the period, going from left to right. And then, like I said, it's fairly logical. As you go down, they're getting bigger. You're adding on more and more and more energy levels to the outside. So here you go, another picture. So lots of ways for you to get this information. Okay, now we're going to talk about ions. So all of the stuff we've talked about thus far, talking about atomic radius, we have been talking about neutral atoms. But ions have slightly different radii, right? They follow slightly different rules. So positively charged ions are formed when an atom of a metal loses one or more electrons. We know that. This will be smaller than the corresponding atom, okay? And the way that I like to think about this is like they are cute little kitty cations, right? Cations, cute little kitty cations. Oh, look how cute they are. They're so little and tiny and cute, right? I know it's silly, but that's how I remember that cations are smaller. Let's think about, we were just talking about magnesium, so let's talk about magnesium. So this is my nucleus, and there are, 2 electrons in the 1s. There are 8 electrons in the second energy level. I'm putting together the 2s and the 2p. And then in the outer energy level, we have 2 electrons in that 3s. Okay, so this would be neutral magnesium. And so when magnesium loses, let's say magnesium loses 1 electron, which it doesn't, right? Magnesium loses 2. But let's just say for this particular example, let's say it lost 1 electron. Say it lost this one. And when it loses that electron, now this electron over here is not experiencing as much repulsion from the nucleus. Okay, it's not experiencing as much repulsion. It's going to be more attracted to the nucleus, and it's going to be able to be drawn in tighter. And so that will happen for each electron that you pull off. All of the other ones will be, all of the other valence electrons will be better able to be attracted to the nucleus because they're not being repelled by these other electrons. Even though in this diagram they look really far apart, remember that electrons are like zooming all around and doing their own thing, and at some point they will end up close to each other and they will experience repulsion. So if we pull this electron off, then the other electron is not experiencing as much repulsion, and it can draw in closer to the nucleus. If magnesium then lost both of these electrons, right, if it lost both of them, it's going to lose that entire outer shell. It's going to lose all of that 3s, right? And so then its outer shell would be this second energy level, which naturally is much closer by default to the nucleus, which makes it smaller than the corresponding neutral atom. So cations, right? Cute little kitty cations. They're little tiny. They are smaller than their neutral atom. Anions, we know negatively charged ions when they are gaining electrons, and they will be larger than the corresponding atom for a similar reason, right? So let's say we had something like this. We have, our 2s electron or our 1s electrons, and let's say we have 2s2 and 2p, 5. 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 electrons there. And so this would be fluorine, right? So if we add another electron, if we're going to add another electron here, all of these other electrons will now experience repulsion from that electron and all the other ones that were there already, but they're going to experience even more repulsion. And to account for that repulsion, they're all going to kind of spread out. They're going to get farther from the nucleus so that they can, space themselves out enough, essentially, so they all have enough room. And the only way that they do that is kind of by backing off, by making that 2p orbital larger, right? They're going to get farther out to allow for enough room for the repulsion. So anions will be larger than the corresponding atom because all of these little repulsions, right? Because the added electron or electrons, right, will repel the existing electrons and make the atom larger. So here we have radii of atoms and their cations. So on the left for each one of these in gray is going to be the neutral atom. And then on the right for each one in like that purpley color will be the cation. So you can see that the cations are always smaller than the neutral atoms. And if you look, right, the more electrons that these atoms lose, the smaller and smaller and smaller they become. So like Li plus lost 1 electron, where E3 plus lost 3 electrons. This is going to be a much smaller atom. So the more electrons they lose, the smaller the atoms will become. Okay. So there you go. So cations, a lot smaller than the neutral atoms. And so the trend is that they will get bigger, going to the left and down, just like the radius. Anions are larger than their neutral atoms. So on the left in gray, we have the neutral atoms, and on the right in green, we have the anions, so the ones that they have gained electrons. Okay, and so again, the more electrons something gains, the larger it will become. So we have these trends. I know it's hard to tell in the picture, but you can look at the numbers here, right? The fact that oxygen gained 2 electrons made it bigger than fluorine only gaining 1. Not as big of a jump, right, for all of these, but still, the more electrons they gain, the larger they will become. So here's another picture, another diagram of ion sizes, right? If we look at the cations on the left, remember the more electrons they lose, the smaller they are. For the anions on the right, the more electrons they gain, the bigger they are. So go ahead, pause, try this out. Choose the larger of each pair. So in going over this, S versus S2 minus, right? The anion is always going to be larger, right? As we gain more electrons, we have to account for that repulsion. And so when we gain 2 electrons, that atom gets bigger. The opposite is also true, right? If we lose electrons, the atom gets smaller. So in looking at the next one, right, calcium 2 plus is going to be smaller than calcium, and calcium 2 plus will actually be about the size of argon. So it's actually going to be a lot smaller than calcium, because argon, if you'll recall, is the smallest atom in the 3rd period, right? Because it's a noble gas, so it will be really, really small. And calcium is one of the largest atoms in the 4th period. So calcium will be larger here. And then bromide versus krypton. So if we think about neutral bromine versus krypton, right? This is our trend for how to find the biggest atomic radius. Atomic radius increases going to the left and down on the periodic table. So francium is our largest element, right? I think of it as big fat francium, right? That's our big element. And our smallest element is helium. So if we think about bromine and krypton would sit about here if this is what the periodic table. So normally bromine would be larger than krypton, following the arrows, right? They get bigger as you go to the left. And so if bromine gains an electron, that made it even larger still. So bromine will win here. So the next trend we are going to talk about today is ionization energy. So ionization energy is the energy required to remove an electron from an atom. So it's how much energy it takes to pull off a valence electron, pull off one of those electrons from the outer shells. We're not going to remove core electrons. They always come off from the outside first. So it's how much energy it takes to remove a valence electrons. So it increases for successive electrons taken from the same atom. So what that means is that, the first electron may be easy-ish to take off. The second electron will always be harder. The third electron will always be harder. The fourth electron will always be harder. Okay? And the reason for this, right, as we pull off, think about if we pull off 1 electron, right? And this is kind of what I was talking about with respect to magnesium earlier. If we pull off 1 electron, then the other electrons are not being repelled by that electron we pulled off. And as you pull off more and more and more electrons, the remaining electrons are able to be more attracted to the nucleus. So the ionization energy tends to increase going across a period. So as we go from left to right on the periodic table, we are getting a higher and higher and higher energy. The reason for this is that the effective nuclear charge increases. Okay, we're having more and more and more protons in the middle, which when we do our effective nuclear charge calculation will make our effective nuclear charge larger and larger and larger, which means that all of the electrons in the atom, especially those valence electrons, are being more strongly attracted to the nucleus as we go from left to right, because that larger effective nuclear charge. We will have some irregularities, which we're going to get into, at half-filled and filled sublevels because of this repulsion that's going to happen. And like I said, I'm going to talk about that more in a minute. But at half-filled and filled sublevels, we have some extra repulsion that's happening because of paired electrons and orbitals that makes them easier to remove. So the reason I'm bringing this up is because it's not like the radius where from left to right it got smaller at the end. This is why it says it tends to increase going this way. It doesn't always, there's a couple exceptions, but it tends to increase because the effective nuclear charge increases. And as we go down a group on a periodic table, the ionization energy decreases. And this is because the outer electrons, right, those valence electrons, if we think about francium is a big, huge atom. And those outer electrons are really, really, really far from the nucleus. They are experiencing very little attraction to the nucleus. If we're thinking about Coulomb's law, right, we have a very, very large distance from that nucleus to that electron that we're talking about. And so a very large distance will make a very low force of attraction. And since it's a very low force of attraction, it has a very low ionization energy. It's really easy to pull off electrons from large atoms because they are far from the nucleus. So here's a picture to show the trends in the first ionization energy. Since helium is the smallest atom, it has the highest ionization energy. It is extremely hard to remove an electron from helium. You don't ever hear anyone talking about like He+. It just doesn't happen. Helium does not want to give up its electrons. Right? And that's true for most of the noble gases. This is why they don't participate really in bonding, is because they have extremely high ionization energies. There's no one that's going to take off one of their electrons, right? They're going to hang on to them for dear life. If we look down here at cesium, right? We don't have francium on here, but we have cesium. Cesium is the largest element that's shown on this graph, right? Our elements get bigger going to the left and down. So cesium is the largest element. That means its one little valence electron that it has is extremely far away from the nucleus, right? It's not experiencing very much attraction because of all the shielding from those core electrons, right? There's a ton of electrons between that valence electron and the nucleus. So it's experiencing a ton of shielding. It's not being held on very well, and so it has a very low ionization energy. So it's extremely easy to pull an electron off of cesium. So again, our increasing ionization energy as we go to the right, we are getting a larger effective nuclear charge, right? This trend has to do with ZEF. And like I said, because there's more of those protons in the nucleus, right? And we're not getting, like as we go this way, we're not getting more core electrons, right? The number of core electrons doesn't change. We're changing the number of protons, but not the number of core electrons. So the way that we calculate Z effective is going up as we go from left to right. And so those valence electrons are experiencing a greater attraction to the nucleus. And when they experience a greater attraction to the nucleus, they're being held on tighter, which makes them have much higher ionization energies. Okay, so that's kind of the thought process between this whole thing. So ionization energy is the minimum energy needed to remove an electron from an atom or an ion. That's the technical definition. And the way that we write these reactions, we're always going to write them in the gas state. And we're going to get more into this soon when we get into bonding. This is an endothermic process. Okay, it requires you to put in energy to pull off an electron. Electrons don't spontaneously just fall off these atoms, right? You have to go in and pull them off. So it's an endothermic reaction. Energy has to be put in to pull the electron off. If you have an electron that is easy to remove, that means it has a low ionization energy. You can think about this as like an energy cost, right? If we have a really big atom like cesium or francium, those electrons aren't being held on very well. They are really far from the nucleus. They're experiencing a lot of shielding. The atom's like, take it or leave it. I don't care. Take my electron, right? It has a low energy cost to pull that off. So that's why it has a low ionization energy. And so these M's here that you're seeing in these reactions, it's not supposed to be magnesium. It's just supposed to be M for metal. So the way that we would write this, because it's an endothermic process, we are putting ionization energy on the left. So M plus some energy, right? So a metal plus some energy will allow us to pull off one electron. And we get M plus or M1 plus and one electron floating around by itself. And then if you wanted to pull off another electron, you could go M1 plus, you could put in some more energy, more ionization energy, and pull off another one. Just remember that, the IE1, right, it may be okay to pull off one electron, but the first ionization energy is always smaller than that second ionization energy, which again would be even, smaller than the third ionization energy. As you pull off more and more and more electrons, the ionization energy gets larger and larger and larger. Again, because those remaining electrons are experiencing more attraction to the nucleus. So as we go from left to right, ionization energy increases. Again, that's because of that effective nuclear charge. And as we go down on the periodic table, our ionization energy decreases. And this has to do with atomic radius, right? Because those exterior electrons are so far from the nucleus, they are not experiencing as much attraction. It's much easier to pull them off. So here's our trends in successive ionization energy. So this is, if you remove one electron, then two electrons, then three electrons. Again, like I said, it's always easiest to remove the first one. It gets harder to remove the second, harder to remove the third. So there's reasons for this. So one, like I said, was the shrinkage in size. If you pull off one electron, then the atom gets smaller because the remaining electrons are not experiencing that repulsion. And they're going to be more attracted to the protons in the middle. They're being, now the protons outnumber the electrons, and they're able to draw them in really, really close. As they draw them in closer, right, these outer electrons that are now closer to the nucleus are then harder to remove. So as you remove electrons, right, the remaining ones get closer to the nucleus, making them harder to pull off. This graph over here on the left, I want to spend a minute and talk about that. As you'll see, the first ionization energy for sodium, right, is really low, right? And then it gets really high, really, really fast. Whereas magnesium, the first two are fairly low, and then it jumps up really crazy. So here's what's happening. So if we think about the electron configurations of sodium and magnesium. So sodium is 1s2, 2s2, 2p6, 3s1. Right? Sodium has one valence electron, and it's fairly easy, right? This 496, it's fairly easy to pull off this one valence electron. But as you try and pull off another electron, now you're trying to pull off a core electron, right? And these core electrons are being held much more tightly than that valence electron was. So to pull off one of those core electrons requires a ton more energy. And so you can actually use graphs like this to figure out how many valence electrons something had. The fact that it was easy to pull off one electron, but really hard to pull off a second, tells us that this atom only had one valence electron. If we look right over here at magnesium, These two are fairly easy to pull off. Again, the first one's always easier to pull off than the second, right? But these two are fairly easy to pull off compared to this third one. This would tell us that even if we didn't know that it was magnesium, that this atom had 2 valence electrons, because the first two are easy enough to pull off. That third one is crazy. And again, that's because, right, 1s2, 2s2, 2p6, 3s2, right? Magnesium has 2 valence electrons. So the first one is easy enough to pull off. The second one's okay because they're both valence electrons. But as soon as you pull off 2 valence electrons, and now you try and pull off a third electron, that third electron is going to be a core electron, which is much harder to pull off. This is another, another way of showing it, right? The blue ones are valence electrons, and the pink ones are core electrons. If we look at aluminum, right, 578, 1820, 2750, right? Those are similar enough. But then we get this jump from 2750 to 11,600. That is a large jump. So if I ever ask you, if I show you some data like this, and I'm asking you to figure out, how many valence electrons does something have, you're looking for a huge jump in value, that it's jumping over like 10,000. And if it jumps over 10,000 kilojoules per mole to pull off one of these electrons, then that's probably signaling to you that this, is a core electron, whereas this was a valence electron. So now we're going to get into these irregularities. So this is just showing first ionization energies here. And the general trend is that as you go from left to right on the periodic table, the ionization energy increases. So if you'll look just in general, right, going from like lithium to neon, overall it increases. Sodium to argon, overall it increases. But in the middle, we've got some weirdness happening, right? It doesn't always increase. The overall trend is that it increases, but it doesn't just straight increase. It's got these little dips that happen. And so these are the irregularities that I was talking about earlier. So we're going to talk about each one of these. These two happen for different reasons. So we're gonna talk about those. First, we're going to look at beryllium and boron. On the left, we have the neutral atoms, right? We have beryllium, we have 1s2, 2s2, it's got empty 2p's, right? And then boron has 1s2, 2s2, 2p1. So if we look back here, if we were going just from left to right, we would think boron should have a higher ionization energy than beryllium, going from left to right, but it doesn't. Beryllium has a higher ionization energy than boron does. So we need to figure out, why is beryllium higher than boron? And so when if we were going to ionize beryllium, right, if we were going to pull off this electron, to ionize this beryllium, we have to break up a full sublevel. And when sublevels are full, they are particularly stable. When sublevels are full or half full, that's kind of what we were talking about with electron configurations last time. But to break up, or to ionize beryllium, we have to break up this full sublevel, and that costs a lot of energy. Whereas when we look at boron, boron's got this one little electron hanging out by himself in this 2p energy level. And if we ionize boron, what we've done is we've taken that one away. Right? And when we take that one away, we actually get a full sublevel, which is desirable, right? So to ionize beryllium, we have to break up a full sublevel, which costs a lot of energy. This is not desirable. When you ionize boron, though, you get a full sublevel. And so this costs less energy. Beryllium is harder to ionize than boron is because of this full versus, not full sublevels. Our other one that we're going to look at is nitrogen versus oxygen. So again, I'm going to pop over here. So nitrogen versus oxygen. Again, going from left to right, we would think that oxygen should have a higher ionization energy than nitrogen because it's farther to the right on the periodic table. But what we see is that nitrogen has a higher ionization energy than oxygen does, which is weird. So it's harder to ionize nitrogen than it is oxygen. So if we're looking at ionizing nitrogen, we have a half full sublevel, right? And like I said, things are particularly stable when they have full or half full sublevel. So to break up nitrogen, we have to break up this half full sublevel here. This requires us to input a lot of energy to pull off that electron. Whereas if we look at oxygen, if we, take off this electron here, right? And this electron is being repelled by this electron. They're kind of sharing the space, right? They're sharing that orbital. And since they're sharing that orbital, they're experiencing a larger amount of repulsion, making this electron actually fairly easy, comparably to pull off. And when we ionize oxygen, we get a half-full sublevel, which again is particularly stable. So this costs less energy for these two reasons, right? The main reason here, though, is because this electron is easier to pull off than it should be because it's experiencing repulsion from its neighboring electron. And when it gets pulled off, we get this half-full sublevel, which is desirable. So nitrogen ends up having a higher ionization energy because it is harder to pull off this electron and break that half-full sublevel than it is to pull off this electron, which is experiencing repulsion anyways. So these are the two exceptions to the first ionization energy trend that I need you to know. If I'm going to ask a question about ionization energy, right, it's going to be this beryllium versus boron, or it's going to be nitrogen versus oxygen. You see it happen also over here, but just to a much smaller extent. But it's for the same reasons. But probably if I'm going to ask you a question, it's going to be beryllium versus boron and nitrogen versus oxygen. So that's it for this set of slides. So we have now finished part 2 of chapter 8. Please send me any questions that you have.